So our next speaker is Kristian Joten Andersen. He's also a PhD student in Oslo, and he's going to talk about foregrounds in temperature intensity. Please go ahead, Kristian.
Thank you, Ingunn. Hi, my name is Kristian Joten Andersen, and this talk is going to be a follow-up of Trygve's talk, which will be based upon some of the equations that he derived. But now we're going to talk about the intensity foregrounds and the component separation tricks that we use in order to be able to constrain the components as well as possible within the pipeline with a reduced data set that we have. So, as you've seen already many times by now, this is the BeyondPlanck data model for the LFI 2D data. And as Trygve mentioned, we are sampling this amplitude and the spectral parameter when we do the component separation. Now, again, just for a simpler notation, when sampling for the components, we're basically mapping out the posterior distribution of the amplitude and the spectral parameter given all the other parameters data. And we now just abbreviate this to posterior distribution of A and B with respect to data and just omitting the other parameters for now, assuming they are constant. Now, so also Trygve showed this can be written with Bayes' theorem as the likelihood function and the priors, and we'll get to the priors later. Normal Gibbs sampling, though, would then be conditionalizing on this, these two functions or distributions and drawing samples from them. Now, with polarization, this is easy enough as the potential correlation between the spectral parameter and the amplitude is quite low, but in intensity, we have a really high signal to noise ratio, and thus the likelihood function becomes extremely highly correlated. And in the case then when you try to Gibbs sample drawing from the only from the conditionals, you get a really slow moving across the entire joint likelihood function. And thus it takes the Gibbs sampler a really long time in order to converge or in order to map out the full posterior distribution in effect. Now, mathematically, we can also write this as this joint distribution as a product of the conditional distribution of the amplitude with respect to the spectral parameter times the marginal likelihood of the spectral parameter. And if we are able to find a way to draw from this marginal likelihood of beta, that is described here in blue, we would be able to sample out this entire joint distribution a lot faster than with standard Gibbs sampling of these two regions. So, and it is really important to mention here that you have to always sample on the marginal likelihood first, because if you first sample the conditional, if you first sample on the conditional of A with respect to beta and then sample the marginal of beta, you lose all information that you had on the amplitude and the entire sampling breaks down. So as Trygve said, we have the data are in component separation is the sky maps at a given frequency with some mixing matrix containing the spectral parameter and the amplitude of the components. Now, the log likelihood of this can easily be written as a constant then times the chi-square given by this equation. And we assume that this to be Gaussian white noise. So, but now we do three assumptions that in order to increase the computational efficiency, and that is that beta varies more slowly than the amplitude across the sky. In addition to that, we assume that that we have uniform pixelization and angular resolution for all the sky maps. We can do this internally in Commander, although because we have the sky maps at different resolution, but we can internally smooth them to the same resolution and degrade them to the same pixelization when we sample these parameters. And in addition to that, we also assume that the noise covariance matrix N here is diagonal. If we do this, Stomper et al. Showed that per pixel, meaning the same pixel across all the sky frequencies, the marginal log likelihood that then falls down into, we get this equation here, where this last term is just the logarithm of a determinant of this matrix here, which is easy enough to compute. And this second term here, which is the same as the ridge likelihood function. And the ridge likelihood function is as simple as the maximum conditional likelihood of the amplitude for any given beta. So, and knowing this likelihood, this marginal likelihood function, we can sample it in the same way as we sample for the conditional in polarization, and we can solve the amplitude with the same CG algorithm as we did for polarization as well. So now we're going to look at the data model and the priors that we implement in order to constrain our model. In short, we implement the same components as the 2015 analysis, Planck analysis did, having then the CMB, the synchrotron, the free AME as a spinning dust model, the thermal dust model, and point sources. Now, the point sources were not included in 2015, but included in 2018. And as the component separation code builds on the 2008, the one used in 2018, we can include this one as well. So all the free parameters that we actually do sample is here marked in blue, meaning all the amplitudes, with the exception of this amplitude here, which is the kinematic CMB quadrupole, which we just remove as a template from the files, but we still keep the kinematic dipole in the maps. We do not include the Sunyaev-Seldovich effect, the zodiac light emission, or the cosmic infrared background, as these are more, we don't have the signal to noise with our setup in order to constrain these parameters, and their effect at the LFI frequencies is almost negligible. So what data do we use in our analysis? Trygve mentioned some of them. We use the Planck LFI data, the TOD data that we've been to the pixelized map following Anastina's talk yesterday. We also, in temperature, include a Planck 857 gigahertz map in order to constrain the thermal dust intensity. We include the W map 33 through 61 gigahertz maps in order to better constrain the set of low frequency foregrounds. And we also include the Haslam map at 408 megahertz to constrain the synchrotron intensity. And similar to what Trygve mentioned, we do not include the Planck HFI nor the W map 23 gigahertz data because they have a higher signal to noise ratio than Planck on these on the foregrounds that we model. And we, in the BeyondPlanck collaboration, it is a show of the algorithm itself. So we want the LFI data to be the primary driver of the statistics. And because we do not include this data that we have available to us, we are more prone to degeneracies between the components, and we're completely clear of that. And the best way of showing this is at the galactic south pole between the AME component and the free component, where we expect both signals to be very close to zero. But we see here we have a really large fluctuations in them. And if I flick in between them, you'll see that they are almost perfectly anti-correlated. So they, on average, they will cancel each other out at most of the LFI frequencies, but at slightly lower or slightly higher multiples, we see there is a difference. And this difference will then be degenerate with the other sky components, in this case, probably being sucked up by the CMB. And these fluctuations are quite high. Now, this is not ideal, and in order to limit this, we implement amplitude priors for the two components, the free and the AME. And we then use prior mean maps based on the Planck 2015 free map, and assuming that the spinning dust traces the thermal dust in morphology, we scale our dust tracer map, the Planck 857 GHz map, so that the amplitude more or less where we have a high signal to noise has about the same amplitude as the AME map, and then we can implement an RMS that in the spherical harmonic space in the power spectrum that has a amplitude prior Q and a pivot, a tilt parameter beta here that can either allow us to have larger or smaller RMS at higher multiples. And in the case of free that is a lot more fine structure, we need to allow for a higher RMS at higher multiples, and therefore the prior that we use marked here in the green intersection, the lines of the green intersection show that we use a beta of 2 for free, while a flat prior for the AME component. And these prior are chosen so that at high angles where we have small signal to noise, we don't see a large increase in the chi-square when we apply these priors. So looking at how these priors affect the maps is that we show again these high multiples at the South Pole, and we see that for a realization when we use the prior, these fluctuations are heavily reduced. Now we still have some anti-correlation in between them, and there's still some difference in the overall multiple powers, but we reduce the power at least a little so that we don't get that much degeneracies with the CMB. For the spectral parameters, on the other hand, we are also prone to degeneracies between the parameters, and thus we also decide to fit a full sky value for each of the spectral parameters, and we choose to fit them only in areas marked here in white where the signal itself has a high amplitude, but is still over some lower threshold. But we also exclude areas where we have high amplitudes of the other components in order to try to limit the degeneracies in between the priors as well. A coarse grid sampling of these parameters shown here, where we have multiplied the prior that we end up using with 100 for the synchrotron and the peak frequency of the spinning dust model. We see, and emphasizing here that there is a huge difference in the overall values here, showing that for the synchrotron beta and the AME peak frequency, these parameters should be well constrained by the data and should be completely data driven. While in the case of the dust beta, it's less constrained by the data, and also this is just a coarse sampling with all the other parameters frozen. When we try to sample all of them using the data, we saw that the dust beta went to high values, larger than 2, which is not physically motivated at all. And this is because we have a really few data sets that cannot really constrain the parameters, and therefore we choose to only sample this dust beta parameter in the same way as we sample these degenerate regions in polarization by only sampling it from the prior. This is in order to allow for the uncertainties of the priors to propagate through the entire pipeline. And the priors are from the Planck 2015 analysis effort, with the exception of the AME peak frequency, which we set with a mean at 28, but this is primarily signal driven, so the prior mean shouldn't do that much for the sampling of the parameter itself. In addition, the point sources has a spectral index individual for each point source, and those are sampled with this prior following Bennett et al. While the free component requires an electron temperature that we could fit, but a change in the electron temperature doesn't do that much to the spectral energy density of the free map. And we choose for this analysis, at least, we chose to freeze it at the prior mean of the Planck 2015 analysis. And when it comes to the thermal dust, we don't have any maps that can really constrain this, and we use the most recent Planck HFI results as our thermal dust temperature prior. So let's talk a little bit about the results that we see. Now, first, we have a look at how the spectral parameters actually change through the samples for each of the chains. And what we see immediately is that there is a really long burn-in time for the AME frequency. And this is because we initialized these runs on a previous pipeline that only sampled the AME frequency, then with a spectral parameter of the synchrotron at the prior mean. Now, when we sample these and we see that the synchrotron beta also changes, this one changes as well. So, and we only see if it flattens out more or less only the last 50 samples. So it's only the last 50 samples that we include in the results effectively. The dust beta is just following the prior, which we said, which is what we expected to do. While for the synchrotron beta, the spectral index of the synchrotron map, it really doesn't change that much, but we're also not sampling it. It's just drifting slowly. Now, effectively, we have more or less frozen this beta over all these samples on a value of around minus 3.08. But it's clear that this beta is, that the uncertainty is completely underestimated. So, and we have some hypotheses of why this can be, and some of them are maybe we have a poor choice of pivot frequency that correlates with other components, so that the entire correlation length between samples gets really, really, really long. Another thing is, and in that correlation, we believe that it might be a strong correlation with a free component, where we don't even fit for we have a constant electron temperature that we don't marginalize over. And a third hypothesis that we have is that we're also not marginalizing over the Haslam monopole, and even a small monopole in the synchrotron map arising from a badly fitted monopole in the Haslam map can also lead to really strong restrictions on the spectral parameter of the synchrotron map. And all of these hypotheses we're aiming to investigate in new pipeline runs for the data itself. So looking into the low frequency amplitudes. Now here we see on the left the AME, the free, and on the bottom the synchrotron amplitudes. At first glance, they might look quite similar to what we've seen from the Planck results. Now, if you look at the difference map with respect to 2015, it looks very differently. Now, in the case of AME and free, we almost see a completely the same morphology. One, the blue in AME and the red in free, and this is a clear sign that we have definite leakage and definite degeneracies between the parameters. So the AME having a lot of amplitude and power leaking into the free component that we're not able to take out with the applied amplitude prior. In the case of synchrotron, we see that we have a really strongly blue galactic plane, and this might be because there's a difference in the spectral index in between the two. And in addition, we as literature has shown lately, there is expected to be also difference in the spatial difference of the synchrotron in as the spectral index of synchrotron, which also might give us some possible improvements in the future if we're able to sample it with different regions, as we did for the polarization run. Now, we also see in this difference map, we see clear blue dots, and these are just the result of us taking out point sources, while 2015 did not. Now, we can also see this in our residual maps, being a good estimate of the goodness of fit for the LFI maps on the left and the W maps on the right here. And we see this AME, this dust and in partially free morphologies of the residuals, blue and red imprints here, showing again that there are clear degeneracies between the two the two components that we are not able to constrain with the data set that we have. Outside these, where these components dominate, we see that almost all the maps are consistent with the white noise at the fluctuation level of the maps themselves. So looking at the thermal dust emission, we don't really see that much difference with 2015. The only really clear thing at higher latitudes is this band here, this orange band following the ecliptic plane, which is which we would believe is simply because we don't model the zodiacal light emission, except for just subtracting a template from the 857 map. And at 545, this has a value somewhere between 3 and 10 microkelvin, but the zodiacal light at the LFI frequencies has an average of less than half a microkelvin, and it's not going to affect the final results that much. So therefore, we find this to be satisfactory. Now, here looking at the compact sources, the point sources that we model here, as seen by the different LFI detectors, we see that the overall amplitude is falling with frequency. This is completely consistent with a effective negative spectral index, which on average lies around minus 2.3, 2.5. But another thing that we see is that because the lower frequency detectors has a wider beam, we see that the signal itself is more smeared out. It's wider on the sky. And then finally, to look a little bit to the future here, this is our data model as we've used in this analysis, and we have the Hassler map all the way out here in order to try to constrain the synchrotron intensity that goes up here, and the 857 band here to take the intensity of the thermal dust. But then we're just with these 6 bands here that covers a really short frequency range, we're trying to constrain all the other parameter, all the other components here, and it shows that we are extremely susceptible to degeneracies, and it's not possible to constrain them well. So in the future, we would like to add on new data set within the BeyondPlanck pipeline, so treating all the data in time, so that we can resample and have all the uncertainties propagate. And in that case, we can add more or less all the data we want. Now, we're at the moment, we're limited to the amount of data that we can store in memory, and therefore also our set is quite low. But if we were able to include Planck HFI to sample the dust beta and the free component a lot better, as well as adding Derby to take the high end sampling thermal dust temperature, we can also include the C-bas, S-bas, and chi-bas data in order to better constrain the synchrotron spectral index, and hopefully also re-add the WMAP K-band in order to also better take out the spinning dust. So, and this entire thing is one of the main goals of the Cosmoglobe project that Ingun will talk about later today. So to summarize, we have included a marginal likelihood sampler in order to allow for faster sampling between correlated posteriors. We have also included amplitude priors because we need to reduce the degeneracies between the AME free and CMB components. We also apply spectral parameter priors, and also just sample from priors in some cases. This is in order to constrain weakly determined parameters while still allowing us to propagate errors through the entire pipeline, or not errors, uncertainties throughout the entire pipeline. What we've seen from this analysis is that there are clear degeneracies between AME free and to some extent synchrotron amplitudes that can go into the CMB component. And the only way that we can really constrain these better is to include more data sets. So, and additionally, we have also seen that for the spectral parameter sampling of AME and synchrotron, we have a really long burning time, and we're working on with hypotheses of how we can improve these, where optimizing pivot frequencies are one of them. And this is a work in progress, and we're going to look at in the near future. So, and the next step in the future would be to populate this entire analysis with as many data sets in order to break the degeneracies and constrain the entire model. And again, this is the main goal of Cosmoglobe. I would like to thank our funders, the European Union Horizon Project, for the grants. Without their funding, this project wouldn't be possible. And if you have any questions, now would be the time to ask them.
Thank you, Kristian.